not to confuse us too much. So again, if I write Sx, I can write the function expressing the number of independent functions on x of degree d, so to speak, hsx, the Hilbert function of d, that's the dimension over k of the degree d part of Sx. And Hilbert's theorem, which I'll prove for you in a moment, is that hsx of d is equal, for d sufficiently large, to p x of d, a polynomial. And of course, the algebraic geometers recognize this polynomial as chi of ox of d. And the family up there is flat in the situation I've written it, or even over any reduced base. X is flat. Those are the families that Karen told us were the good families, if and only if this p x sub p, as I've written it there, of d is constantly equal to some polynomial p of d. It doesn't depend on the point little p. So somehow this Hilbert polynomial is the invariant. It's not just a sort of arbitrary collection of numbers that you might make out of a projective variety and then think, is that interesting? It is the invariant which tells you whether families are flat. It's the thing that tells you that varieties belong together. Now, from an algebraist's point of view, we might ask a different question. We might ask when this family of rings that I've defined, really, by this object is a ring, right? And I get a new ring for every point p. You might ask when that's flat. And that's flat if and only if the Hilbert function is a constant. So theorem, the family S xp is flat if and only if h sx of d is constant. So from this point of view, it's rather natural to try to look at what this Hilbert function is and what it means, and try also, since flat families are still rather large and contain varieties with all kinds of different properties, it's rather interesting to ask what the properties of individual ones are. In other words, can we find some invariants which strictly refine this Hilbert function? And the invariants that I want to talk about are exactly of that kind. So we should think of them as a way of refining the Hilbert function. So let me back up now and prove that the Hilbert function is eventually a polynomial using Hilbert's original proof, and that will take us to the invariants that I want to study. So theorem M, let's say it's a direct sum of M sub d, a graded module, I'll stick with this notation forever. Then if M is finitely generated, then the Hilbert function hm of d, that's by definition the dimension over the field of M sub d, is polynomial for large d. That's the way this is usually stated, but actually the theorem that you always prove is much stronger, or at least the theorem that you prove the way I'm going to prove it, and it gives an actual closed form version of the function itself, from which you see immediately that it's a polynomial for large d. So polynomial for large d, let's say, and more. We'll see that in a moment. So how do you prove it? Well, Hilbert's idea This is not the proof that's in lots of modern textbooks. Hilbert's idea was to compare M with a free module. So let's think first about the free module. What is the Hilbert function of a free module? Well, of course, the free module is a direct sum of rank 1 free modules, so you might as well think about the rank 1 case and then add them up. So how about a rank 1 free module? There are more of those than you might think in this situation because we're looking at graded modules. So you have to distinguish the rank 1 free modules by what degree their generator is in. Otherwise, of course, they're all the same. So I will write S of minus A for the rank 1 free module with generator in degree plus A. What an awkward choice of notation, right? But it's justified by the general formula M of B in degree D is equal to M in degree B plus D. So if you think about this formula, you'll see that this is the right notation. Okay, and let's write down the Hilbert function of this module, HM. Well, of course, it's just the translation by A of the Hilbert function of S. So we might as well write down the Hilbert function for A equals 0 first. HS of D. All right, so how many monomials are there in degree D in a polynomial ring with R plus 1 variables? Well, if you line up the factors and sort them by increasing index, then you get a weakly decreasing sequence in degree D of D numbers less than or equal to R, right, between 0 and R. And now if you add I to the ith one, then you get a strictly increasing sequence of numbers less than or equal to R plus D. Actually, R, and there are R plus 1 plus D choices of the index because I started with 0. So we have D things chosen from R plus D plus 1. Somehow I got an extra 1 in there. Where did it come from? Oh, I added 1 to the... That's right, I added 1 to the first one. So the 0 has become a 1. So this is R plus D choose D or choose R. It doesn't make any difference. Okay? So there's the Hilbert function of S. So the Hilbert function of S of minus A is then just by translation R plus D minus A choose R. And what is this function? Of course, this is R plus D times R plus D minus 1 times R plus D minus 2. R factors all divided by R factorial. That's a polynomial of degree R, because there were R factors in D. Except it's not, because when D is less than R, you're supposed to think this is 0. And it's 0 for all D less than R, infinitely many values. So this is certainly not a polynomial function, but it is a polynomial function as soon as D is bigger than, I guess, minus R. It's a polynomial function for large D in any case. So that's exactly the content of, that's why this isn't a polynomial function in general. That's why it is a polynomial function for large D. That's the whole mystery there. So we could do this now for the direct sum. I won't even bother to write it down. It's just to add these up. And now we have to compare an arbitrary module with a free module. And Hilbert did that by taking a free resolution. So here's M. Choose a set of generators for M. Yeah.
Why can R plus D be less than 0? Because R is the number of variables, isn't it? And D is the dimension. I don't see why it would be less than 0.
I'm sorry, I didn't understand the question.
Well, you were talking about D.
This is a polynomial function. It happens that the polynomial which is equal to this for large D happens to be equal to 0 for a certain number of steps, for a certain number of integer values starting from 0. Think about this. This is R plus D times R plus D minus 1, etc. Right. So if R plus D is greater than or equal to 0, then I have a 0 factor on top. So this is 0. So it actually agrees with the real Hilbert function as long as R plus D is bigger than or equal to 0. Then they just are different.
Yeah, well,
That's an accident of combinatorics.
Well, my question was, why would R plus D be not be greater than 0? Because R is the number of variables.
True, and D is the degree. But no, D is the degree. The degrees could be negative. I could be looking in negative degrees.
Okay.
Right? Well, nothing there, but I could look anyway. It's just convenient to keep that clear and separate. So I take some generators for M in degrees, let's say A I know what's coming, so I'll write them as degrees A0J for varying J, and write here the direct sum S of minus A0J, and think of this as the 0th approximation to M. It's a free module. I'll call it F0. And then Hilbert, exactly for this purpose, proved the Hilbert basis theorem, which said that the kernel of this map, like any other submodule of a finitely generated module, would be finitely generated. So I can repeat the process, choose generators at the next stage, and therefore map a free module onto the kernel, S of minus A1J, summed over J. Call this F1. And since this free module maps onto the kernel of this map, this is an exact sequence. And now I can continue the process merrily until I get tired of it, right? But the great thing is that Hilbert showed that if you do this, after a while, the kernel is itself a free module. That's a kind of magical fact about polynomial rings. What gets better? So why is this image better than this module? Well, you might say it's a submodule of a free module. That's better than an arbitrary module. And that idea can be extended somehow to explain what might be getting better and why this ends. I won't bother with that. But in any case, Hilbert showed that after a while you can stop and you get a free module, F T, let's say, sum over J, S of minus T, A sub Tj. There's some dots in here. And that T can always be taken, that is to say, the kernel will become free. No matter how you choose these generators, no matter what you do, the kernel will become free before you get to T equals R plus 1. This is Hilbert's syzygy theorem. And as I say, it wasn't proved for fun. It was proved for this application to show that Hilbert functions were nice. So let's harvest the result of that, which is that the Hilbert function of M is then the alternating sum, because if you pick out the degree D part of this sequence, it's just a sequence of vector spaces where you take the degree D part of each of these terms. And in an exact sequence of vector spaces, the alternating sum of the ranks is 0. So you can use that to compute the this rank as the alternating sum of the others. And I'm about to write that down. Minus 1 to the I. Well, let's see. It's really going to be here the Hilbert function of Fi. But I can write that as the sum over J of the Hilbert function of S of minus Aij. And I've already written that as R plus D minus Aij. Choose R. All right, and this is a finite sum from 0 to T. And so for large D, this will certainly become polynomial. And you can even sort of see what D you have to take, or what D at least you can be sure if you take, namely D has to be bigger than any of the R minus Aij's. And if you think that smacks slightly of the regularity that we heard about yesterday in group cohomology, it does. It's very closely related. And Jessica Sidman's talk tomorrow, is Jessica actually here somewhere? There she is. Will explain a little bit more of the relation, I think, between where the function becomes a polynomial and these numbers Aij. I might get to that later today. So there's the formula written in a nutshell. And now we see that the Aij are a priori a refinement of the Hilbert function. If you have constant Aij's, then you have constant Hilbert function. Before I go on, let me introduce a different terminology for the Aij's. Somehow there might be many Aij's the same, and it's convenient to collect them and count them. So let me write instead Fi as the sum, again you could think of it over J, but it's a different J, of S of minus J to the beta Ij. So beta Ij is the number, sorry about the coincidence of J's, the number of Aij equal to J. But you have to disentangle the J's. Those are different J's. Yes?
Are you going to say something about the meaning and introduction of the word syzygy?
Syzygy. I wasn't, but it's from the Greek, which means yoking together of oxen. It was used early in history and astronomy for the relation between planets in a line. And I think Cayley introduced it in this context as a relation between polynomials.
So it's things lining up just right?
It's things lining up just right. That's right. Exactly. Oxen, first of all. We haven't seen a syzygy yet, but we will in a moment. So anyway, I have the beta Ij's here, and I'll call these beta Ij's the graded Betti numbers. This is by analogy with the topological situation. We have a chain complex, and these really are Betti numbers. But we'll see that that's more than analogy if I get there today. One can write down lots of examples which come from chain complexes, indeed. So there they are, and let me rewrite this formula in those terms for future reference. It's the sum minus 1 to the I of sum over J of beta Ij times R plus D minus J, choose R. Okay? So there's our Hilbert function written in terms of the graded Betti numbers. Okay, so my thesis is that the graded Betti numbers contain more information than the Hilbert function. Hilbert function, remember, is telling us about flatness. The graded Betti numbers, therefore, refine flat families. They stratify flat families. Now, there's a lot of need for stratifying flat families. Flat families, first of all, if you look at all varieties in projective space with a given Hilbert function, let's say, whose homogeneous coordinate rings have a given Hilbert function, you get a nice flat family. That family tends to have lots and lots of irreducible components. And they're all kinds of horrible components, and they have non-reduced points, and they're singular. All sorts of stuff is going on within that family. So it would be really nice to have a way of dividing up the family into nice small pieces. People have hoped that this was the way, and I have to tell you it's not in general. This is not nearly a fine enough refinement, for example, to pick out all the components of the Hilbert scheme. That's what I'm referring to. But it goes some distance, and there are very interesting geometric examples. And I guess algebraic geometry is, I've always felt, a subject of examples rather than a subject of theorems. It's really built around funny examples and interesting examples. So there are lots of interesting examples in which these invariants carry just the sort of geometric information that you'd like to see next after the Hilbert function, or Hilbert polynomial. Yeah.
I was going to ask you, when you said Hilbert function recently, did you mean Hilbert polynomial?
No, I meant Hilbert function. I'm talking now about flat families of rings. Yeah. But if you want to see them as varieties, then just take cones.
So the betas actually give you the Hilbert function.
The betas give you the Hilbert function. This is the Hilbert function that I've just computed, right? This is on the nose the Hilbert function if you interpret these binomial coefficients as combinatorial objects. And it's the Hilbert polynomial if you interpret them as polynomials, right? It's just a matter of setting lots of terms equal to 0. That's really all it is. So this is the Hilbert function. Now, I thought before I went further, I should stop and do one example in which you actually see something geometric that comes out of the graded Betti numbers, because probably half of you have not seen such an example produced in the flesh. So let me pause and do that. And I guess I now am faced with the need for an eraser. So you'll see more examples of this type, and done probably in more loving detail by Jessica tomorrow. I'm going to give Jessica so many assignments by the end of this talk that, of course, she won't do them all. But this is one that I think she plans to talk about. Let's look at 4 tuples of points in the plane. So if you want to think about that as a family, since this is the beginning of something, let me really write it out as a family of 4 tuples of points. What you do is you say, well, what's the base space? The base space is the space that let's think for 4 distinct points. You can do this with 4 points, a scheme of length 4 if you're into that sort of thing. But let's think about 4 distinct points. So what's the parameter family? Well, it's just a direct product of 4 copies of P2, if I label the points anyway. And but I have to remove the diagonals. So that's the base. And what's the space in which the family lives? Well, it's P2 cross that parameter space. So in other words, I have X contained in P2 cross this funny parameter space, which is P2 cross P2 cross P2 cross P2 minus diagonals. And I'm going to call it T. And then I project to T. And the scheme that I take in here has here the 4 points that are labeled by these 4 points. Right? So that's what it is. And so I can then look, I'll write it down algebraically in a moment, at least in the flat part, the flat algebraic part. So now, first of all, you might ask, is this a flat family? Let's ask that question. And we know we only have to check the constancy of the Hilbert polynomial to see whether this is flat. Is the Hilbert polynomial constant? Well, how do you compute the Hilbert polynomial of 4 points, right? I didn't write down algebra. I'm not about to do all this stuff. How can I compute the Hilbert polynomial of 4 points? Well, let's just look at forms of degree D, and we have to think about those mod the ones vanishing at the points. So we're really thinking about the forms. If we choose homogeneous coordinates for our 4 points, then we can think about the forms as functions on the 4 points, or if you like, dehomogenize. And so we get functions of polynomial functions of degree D restricted on the plane, restricted to 4 points. And we're asking, how many independent ones are there? Now, the set of functions on 4 points is 4-dimensional, right? You could send one of the points to 1 and the rest to 0, and that's the basis. And so in order to get, so that's the maximum number of independent functions we can get. And it's pretty clear that you can interpolate to get any function like that on the 4 points as the restriction of a polynomial. Well, how could you really prove that? You just have to prove that there's a function that vanishes on any 3 and is non-zero on the 4th, which is a polynomial function of large degree. So, well, that's not very hard. Here are the points. And I take some complicated curve going through 3 of them and not going through the other one. That's a polynomial function of whatever degree it took me to do to avoid this last point, vanishing on 3 and not vanishing on the last. So I obviously get all 4 functions on the points as restrictions of polynomials. And you can ask more refined questions about that, and I think Jessica is going to talk about that tomorrow. But in any case, it's easy to see that the Hilbert function, the Hilbert polynomial, is constantly equal to the constant polynomial 4. 4 of D equals 4. Right? So that's the Hilbert polynomial, constant, and therefore this is a flat family. So that's great. But still, there are geometric distinctions between sets of 4 points. For instance, some sets of 4 points lie on a line. Some sets of 4 points have 3 of them on a line. Well, any with no 3 on a line is the same as any other up to projective transformation. So that's where the story sort of ends in this case. That is the natural stratification, is how many lie on a line. Because if 4 points, no 3 of them lie on a line, then after projective transformations, you can always reduce them. So if no 3 on a line, then you can write the points as, after projective transformation, up to PGL of 4. You can write the points as 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1. Right? So there is really only one type of set of points, no 3 of which lie on a line, 4 points. However, there's this other invariant. How many lie on a line? So let's see whether we can tell what these things look like depending on that invariant. And I claim that that's exactly the invariant which shows up in the graded Betti numbers. So this is a pretty trivial example, I think you'll all agree, but nevertheless, it shows that we're looking in the right direction for geometric invariance. So let's just do this. Suppose, let's first take this general case. So for x equals 4 points, and P2 again. Case 1, no 3 on a line. Then what do they look like? Well, I said any 4 were the same as any other 4. There they are. And there you could write them. Well, you know, there's a conic through any 5 points. So there's certainly a conic through 4 points. And there's one parameter family of those things. So if you vary them a little, it sort of stands to reason that you can write it like that. Or if you don't like, if you feel that I might have cheated somehow by just drawing those 2 conics, you could also think of the 2 conics as being 2 pairs of lines. This pair of lines is one conic, Q1, and this pair of lines is the other conic, Q2. And no 3 points lying on a line is exactly what it takes for me to be able to draw that picture. Exactly. So we see from this that we can write down 2 quadratic forms without common factors. Here you see they're without common factors because one is the product of 2 linear forms this way, the other is the product of 2 linear forms this way. So 2 quadratic forms without common factors in the ideal of the points. Now, let's see what the Hilbert function really is and see how many quadratic forms should there be vanishing on this. So Sx, in this case, let me write H sub Sx of D as a table. So here's D. D equals 0. How many constant functions are there that vanish on the 4 points? None. Right? So mod the constant functions that vanish on the points, there's one constant function, and therefore I get 1 as the value of my Hilbert function. Linear forms vanishing on the points. Well, if no 3 lie on a line, then of course there are no linear forms vanishing on the points. So there are 3 linear forms on P2, so I get 3. Quadratic forms. Well, once again, I have to say, can we get every polynomial function, all 4 polynomial functions, by looking at quadratic forms restricted to these 4 points? And it's pretty obvious that we could move a couple of these lines to miss any one of the points, and therefore I get all 4 quadratic functions, and it's the same argument applies to higher degrees. So the Hilbert function has become a polynomial at this step, and it is equal to 4, 4, 4 forever after. Okay, so there's the Hilbert function. Now there's a 6-dimensional family of quadratic forms in 3 variables. 2 plus, yes. So So if there are 4 left over after you kill the ones vanishing on the points, then there must have been a 2-dimensional family vanishing on the points, and we found it. We found 2 independent ones. How many cubic forms are there vanishing on the points? Well, let's see. So again, the number of cubic forms is R plus, this is in this case 2, plus 3. Choose 2. That's 10. There are 10 cubic forms vanishing on the points. So there are, and mod the ones vanishing, there are 4 left over. So there are 6 cubic forms in the ideal. Now, you could get 6 cubic forms by taking the 3 linear forms times Q1 and the 3 linear form times Q2, unless, of course, you got some overlap in those. Could you have gotten an overlap? Linear form times Q1 equals linear form times Q2. Well, by unique factorization, this would mean that this is linear form 1, this is linear form 2. This would mean that Q1 and Q2 have a common factor. Right? L1 can't be the same as L2, therefore it must divide Q2, and then Q2 is L1 times L1 prime. Here's a common multiple which is of degree less than the sum of the degrees, so there must be a common divisor there. So we see that as long as Q1 and Q2 have no common factor, there's no coincidence like this. So Q1 and Q2, the 2 quadratic forms in the ideal of X, generate all the cubic forms. And we could go on with this analysis in some detail and prove that they generate the whole ideal of the 4 forms. So in this case, the resolution looks like this. We have M, which is Sx. We pick a generator, 1 for that module, and map S onto Sx. We've seen that we have 2 quadratic forms which generate the ideal. So I have to pick a free module as generators in degree 2 to map onto each one of those 2 quadratic forms. And then what's the kernel of this map? Well, it should be a rank 1 module. It's pretty easy if you know some commutative algebra to show that it has to be free right away. But in any case, we can write down one relation which is obvious. If I take here Q1, Q2 to be the matrix of this map, then Q2 times Q1 is equal to Q1 times Q2. So Q2 minus Q1 is a relation. And in fact, it's not too hard to show that this is a free resolution. There's an S of minus 4 there. So the graded Betti numbers are beta, let's see, how did I notate this? Beta 0, 0 equals 1. Beta 1, 2 is equal to 2. And beta 2, 4 is equal to 1. And all the other graded Betti numbers are 0. Now, it's rather awkward to write them out this way and say all the rest are 0. It would be much more convenient to have some notation for this. And the standard way to do this, which I think is actually due to Mike Stillman, is now to write down a Betti diagram. Every subject has its own particular flavor. This subject is filled with Betti diagrams. Subjects which are filled with spectral sequences, well, suddenly you get this array of things, and the audience turns off, right? At least the audience who hasn't played with spectral sequences. Similarly, with graded Betti numbers, the audience that hasn't played with these tables a little bit tends to be put off when the algebraists begin to write down these tables of Betti numbers. So this is a place to pay special attention if you don't know this already and understand what's going on. I'm going to notate this resolution as follows. There's the Betty diagram. Now, where did those funny numbers and dashes come from? So this 1, first of all, it's written backwards. That's one of the things that annoys people right away. It's written backwards. That is to say, I wrote that resolution, as people usually do, with the arrows going from left to right. Here, the arrows, you should think of the arrows as going the other way. So the module represented by this column is S. The module represented by this column is S of minus 2 squared. And the module represented by this column is S of minus 4. In general, the columns within the table represent free modules in the resolution, and you should think of the arrows as going from right to left. Now, the things over here just are place markers. They're degrees. I could leave them out. Nothing would change. They're just the numbers from 0 to as far as I felt like counting. The numbers in the boxes are the graded Betty numbers. This one is beta 0, 0. This one is beta 1, 2. This one is beta 2, 4. Why is beta 1, 2 in the 1 row? Well, that's because the lowest degree that a map in a minimal free resolution has is 1, and therefore, when I step back, I expect the degrees to increase by 1, so I've sort of shifted to account for that. So, little digression, what is a minimal free resolution? I didn't say anything about uniqueness of these invariants, and nobody was nervous enough to ask, or maybe you're all just too well educated to ask. But, you know, if I'm going to use these beta ij's as invariants to define something, maybe they should be invariant under something. And in fact, they're not. I could have taken any free resolution to make this computation, and I could get different sets of beta ij's. But it is the case that if I always choose a minimal set of generators for M corresponding to these numbers, a minimal set of generators for the kernel corresponding to these, then the beta ij's are uniquely defined, and in fact, the resolution itself is unique up to isomorphism. Any two of these with the same minimality property would be unique. So this is actually a pretty good situation, but it's convenient to say something a little bit more. I guess I should just erase this theorem. To say something a little bit more systematic, because there's a good notion of minimality for complexes too, which can't depend on choosing minimal generators. So, little digression on minimality. Minimality. So a complex of free modules. What is a complex? It just means a sequence of free modules and maps between them. Possibly infinite. Or let me call this phi I plus 1 and phi I. Phi I in general is the map emerging from Fi. This is minimal if phi I of Fi is contained in the maximal ideal times Fi minus 1. This works the same for local rings. That's why I've written it this way. In this graded case, I like to think of it differently. I think of writing these phi i's out as matrices, and then what this says is that no matrix has an entry of degree 0 in it. All entries have positive degree. So if entries have positive degree, then and this is really a resolution, then the generators of Fi have to map onto things of degree higher than the generators of Fi minus 1. And therefore, I expect the degrees that appear, the twists that appear here, to go up by at least 1 each time. So this Betty diagram takes advantage of that fact to be a little more compact than it otherwise would by putting the things of degree 1 higher in the place immediately behind a given place. So that's why this is spread out. but let's write this out in general. So in general, I would have, if this was the one for the Sx that I had here. In general, if I had a module, I'd write my Betty diagram out by taking whatever degrees I had to. And in the row corresponding to a degree, I put down the number of summands in the free module, but corresponding to that degree shifted by the number of places back. So here goes the Betty beta 0 I. Here will go beta 0 I plus 1, and so on. What? Beta 1 I plus 1. Thank you. Gee, there are lots of awake people. That's good. So in general, you could write down what's in the ijth spot in the matrix. So that's what the Betty diagram is in this case, and I want to write them down systematically so that you sort of get used to this idea. Let me write it up here, however, so that I don't lose so much space. So it was 1, 2, 1. Oh, and the dashes, what are the dashes? The dashes are just a short way of writing 0, so that you don't have to look to see whether it was 0 or just beta written very round. So those are what the dashes are for. You never know what kind of handwriting you're going to meet. Let's see. Okay, so that was case 1, the generic case, so to speak, when all the points are spread out. Yes?
Why is it beta 2, 4 and not 2, 3 then in that third column?
So beta 2, 3 would have been here. Here's beta 1, 2. If I stepped 1 back from that, I would have a degree 3 thing. And I had to go down 1 more step to get beta 2, 4. Right? You can sort of see these are spaced equally in height, just as I went 0, 2, 4, as I went back in the resolution. Once you get used to looking at this picture, it's really a very convenient way of displaying information. But until you get used to it, it's just a nuisance. So that's the, that's the Betty diagram picture. And now let's go on to the next example. Suppose 3 points lie in a line. Three points on a line, 1 off. So the picture is ... There's the line, and there's 1 more point. What's the Hilbert function? Well, once again, there are no constant functions vanishing on some points, so that's easy. Therefore, modulo the ones that vanish, there's 1 left, 1 constant function. How about linear functions? Well, there are no linear functions vanishing on all 4 points. That's what we said. So again, there are 3 linear functions, mod the ones vanishing on the points. How about quadratic functions? There's the interesting place. We saw that there could be 2 quadratic functions vanishing. In fact, to vanish at a point, there's always 1 linear condition on a form of any degree, any point. And it's just a question of whether the conditions are independent or not. So to vanish on 4 points is always 4 linear conditions, possibly dependent. So you always have at least 2 quadratic functions vanishing. And the question is whether there are exactly 2. And to answer that question, you just have to say, is there a quadratic function which vanishes at each triple of points and is non-vanishing at the last one? Well, how about this point? Is there a quadratic function vanishing on all these 3, not vanishing on this one? Yeah, of course. Take the quadratic function to be the linear form defining the line times the linear form defining that line. Right? There's a quadratic function not vanishing at this point. How about if we wanted a quadratic function not vanishing here but vanishing at all the others? Well, again, no problem. Take those 2 lines, and their product is a quadratic function that vanishes at these 3 points, but not at this one. Right? So yes, the 4 points impose independent conditions on quadrics in this sense, and therefore the Hilbert function is again 4 here. Now, it's a trivial exercise. Please think about it if you don't know it already, that once you hit the Hilbert function, in this case, Hilbert polynomial, you'll stay there forever. If 4 points impose independent conditions on quadrics than they do on cubics too. Hint, just add a line far away from the whole picture to see the story. And so we get 4 forever. And what you see is that the Hilbert function is the same as in that picture. So here's an example of a flat family of SX's. Remember, the family of all sets of 4 points was flat. And we see that still you can, it's still flat if you look at homogeneous coordinate rings. The family of homogeneous coordinate rings is flat, at least as long as the 4 points don't lie on a line. If the 4 points did lie on a line, by the way, let me put that case up in parallel. Four points on a line. So then Hilbert function HSX, well, there are still no forms of degree 0 vanishing on the 4 points, but now there is a form of degree 1 vanishing on the 4 points. That was the whole point of having them on a line. So in 1 I have a 2 here. Lord alone knows what comes next. Well, are there quadratic functions vanishing at 2 but not, at 3 but not 4? No, there aren't, right? Because any quadric through 4 points meets this line 4 times, contains the line. So any quadric vanishing at 3 of these points still meets the line 3 times, contains the line, vanishes at the 4th. So again, the conditions imposed are dependent, and instead of getting a 4, we get a 3. And then from cubics on, you can easily see that you get 4. So the Hilbert function is quite different here. And so the family of SX is not flat when you take all sets of 4 points, but it is flat when you take 4 points, not all on a line. So this is a flat family. And what I want to prove in the next 3 minutes is that, in fact, the Betti numbers change. So the Betti numbers successfully tell you the remaining bit of data about the homogeneous coordinate ring, namely whether or not 3 points lie on a line in this flat family. Okay, so what are the Betti numbers? Let's see if we can figure out the equations. There's a convenient way of writing them down. Well, there are actually various ways. Let's look for the 2 quadrics. We know that there have to be exactly 2 quadratic forms vanishing on the points, and so let's look for them for a starter. So here are the points, and I'll write the first quadratic function. Whoops, that's one more point. In orange. So here's a quadratic. Well, any quadratic function vanishing on these 3 points meets this line 3 times, and therefore has to contain the line. So any quadratic function contains the line. And if you want one that vanishes at the 4 points, you can add another line, any line, through the 4th point. So there's a quadric vanishing on the 4 points. And I had some notation for this. So let's call this line A and this line B1. Now, if I want another quadric vanishing on the 4 points, then I can take purple chalk and draw it like this. I'll just draw any other line through the last 4 points. So there are 2 quadrics vanishing on the 4 points. And we know they're exactly a 2-dimensional family of quadrics because we computed the Hilbert function already. So these span the quadrics vanishing on the 4 points. What about cubic forms? Last time we multiplied the 2 quadrics each by 3 linear forms, and we got 6 cubic forms. Unfortunately, if you multiply, so the two quadrics are now, I didn't name the other line. Can you actually see this purple chalk in the back? Bet you can't. Chris, you're a brave fellow. Can you see this chalk? No. Okay. Let me change to white then. Ah, B2. Thank you. So the two quadrics that I have so far are A, B1 and A, B2. And A and B are linear forms. Now, if I multiply these by 3 linear forms and these by 3 linear forms, well, unfortunately, I get a coincidence. If I multiply this by B2 and this by B1, then I get the same thing. That's a syzygy, right? A relation between these two things. But in any case, it prevents me from getting 6 independent cubics. I only get 5 independent cubics. So I need at least one more cubic generator for this ideal. And it's not very hard to see that there are, to draw another cubic and to see that we then do impose independent conditions. Let me draw a cubic. Well, you can certainly have a cubic function going through 3 points on the line. And why shouldn't it go through this point too? Maybe I should have drawn this point somewhere else in order to make it easy to draw. But let's see. So the cubic might go like this, right, on its way to infinity. That's not a cubic. One extra loop in the snake. There we are. There's a cubic. Not a very cubic, but oh well. So there are the equations, and we can write down syzygies explicitly. So let's call the cubic C. By the way, notice that C goes through this point, and this point is actually cut out by B1 and B2. It's the intersection of B1 and B2. So C is a linear combination of B1 and B2. Let's write it as F1 B1 plus F2 B2. Okay? So the F's are quadratic forms. And now the 3 equations, as I've written them down, well, we have 2 equations of degree 2 plus 1 equation of degree 3. So the matrix here is A times B1, A times B2, C. And now C I could rewrite as I said, as F1. Well, let's just think of it as C. What are the relations on that? Well, we saw one syzygy already, namely B2 times AB1 is B1 times AB2. So I can put a B2 minus B1 0 here, and that will be a relation on those 3. What about others? Well, I can't write C as a linear combination of AB1 and AB2, but I could write A times C as a linear combination. So there'll be a relation with an A down here, or minus A maybe, and an F1 and F2 above it. So I can put F1, F2, and minus A, and there's another relation. And in fact, and again, this is something that maybe Jessica will tell you about tomorrow, that's all the relations. So there's a relation which consists of linear forms on quadrics. So that's a relation of total degree minus 3. And there's a relation which multiplies those 2 quadrics by quadrics. So that's a relation of degree 4. And that's the end of the resolution. So the Betty diagram of this will look like this. Here's the 1 for the generator of S. Then for the 2 generators in degree 2, remember we step back 1 and down 1, so we have a 2 here, but there's now also a 1 there for the cubic. And stepping back 1 further, there's a cubic that's sort of degree 1 back from the quadrics there, and a quartic that's 1 there. So there's the Betty diagram for this resolution, and you can see that it differs from that Betty diagram. Well, the only other thing I want you to notice before I stop is that the alternating sum of this diagonal is 0, which is the same as the alternating sum of this diagonal, and the alternating sums of all the diagonals, in fact, are the same in these two diagrams. That's a general fact, and those alternating sums are exactly the data of the Hilbert function. Perhaps we'll come back to that next time. Anyway, this is the first example of a flat family. That's what you're seeing here, a flat family of rings where the different kinds, the geometrically different kinds, are distinguished by their graded Betty numbers. So, thank you very much. Questions? I'm happy to answer. The experts.
I haven't quite formulated this question yet, but if you understand what D points into play.
Yes.
I'd like to know whether the graded Betty numbers distinguish everything you would think of the form, how many points lie on a curve, the Q points lie on a curve with degree R. So
I don't think so, but they take a... thank you. So the question was, how much information do we get for D points in the plane? Well, of course, Rebecca is going to tell you all about that tomorrow, but to say something in slightly in advance, it only captures some of the information that Robin is after. Robin asked, so if you take D points in the plane, then you could make a huge matrix of numbers by looking at the maximum number of those points that lie on a curve of degree E, right? So there's some big collection of invariants there. How many of them are captured in the graded Betty numbers? Answer, some. Unfortunately, it's not complete, but certainly you can tell, for example, what the lowest degree of a curve that passes through all the points is, right? That's the first information of the graded Betty numbers, but that's already in the Hilbert function. And then this shows that you get a little more information than that, and it's somewhere in between.
I have an example of your study where the Betty numbers are the same, but the geometry is different.
I think there's one in my manuscript, but I don't have it in my sleeve. So there is a manuscript. It looks like this. There's a version on my web page now. There will be a better version on my web page this afternoon because I have a more corrected version than what I have here. This is the most corrected version. I'll put it in the library right now. But it's in progress. And the title is The Geometry of Syzygies. It will be a Springer graduate text sometime around next spring, I would guess. Any other questions? Yes.
Yes. Did you consider the generating function associated with numbers?
Sure. So the Hilbert function, you mean of the Hilbert function?
Well, instead of looking at these polynomials, there's something that's a polynomial starting.
Right.
A rational function expression.
Of course. So the other way to write this, and it's the right way if you look at polynomial rings where the generators are in different degrees, is as a generating function. And then exactly the same arguments show that the generating function that you make out of this, so summation hm of d t to the d, is a rational function with a special denominator. In this case that I'm looking at, it'll be 1 over, I guess it's a power series in t, 1 minus t to the r, and then there's a numerator, which can be various things. This is a whole interesting subject, what the generating function can look like, and lots is known in this direction. In some sense, all Hilbert functions are of homomorphic images of a polynomial ring are classified by Macaulay. Macaulay says which are possible, and so in some sense this collection of generating functions is known. Mark Heyman, in his early career, made a specialty of knowing which functions are generating functions of this type, and it's quite beautiful. Any other questions?
Can you write down the Betty diagram?
This is that we have to change the rules so that at least water is allowed in the lecture hall. I'm desperate. So I want to talk some about linear complexes and linear resolutions today. And the first thing I want to explain is why linear free complexes are the same as modules over a different ring, the exterior algebra. So, main thesis in some sense. Remember the notation, let's say S is the polynomial ring on some variables x0 up to xr. And since we're going to talk also about an exterior algebra, let me get notation right away. E is going to be the exterior algebra on the dual vector space. This is, of course, the symmetric algebra on a vector space of dimension r plus 1, which I will call W. So this is sim W. And E will be the exterior algebra on the dual vector space, which I will call V. And the thesis is that linear free S complexes equals graded E modules. And since everything is, in fact, completely symmetrical, I can say linear free E complexes equals graded S modules. So those are the same things. Now, in fact, what I'll define is some functors. I guess I'll define a functor this way called L, since it goes to the left, and a functor, well, unfortunately, it will be the same directions this way because it should be going to the right. And they're not equivalences between these two things because you don't have the same category on both sides. But it's not very hard to enlarge the category in the domain here. If you have a nice linear functor that takes modules to complexes, then of course it will take at least finite complexes to double complexes, and you could make a total complex out of them. So complexes to complexes, morally speaking. And this one also will take complexes to complexes back in the other direction. And now we could have an equivalence, but we don't, because, for instance, we only get free complexes here, and we started with all modules here. However, we could pass the derived categories and get, in fact, equivalences. So they'll be, in some natural sense, adjoint functors on the level of complexes or close to it, and become equivalences on the derived categories. I'm not going to go down that path, as I said, but this is such an important idea that you should be aware that you're seeing a piece of it here. So let me do this. This is not in any sense a deep idea, and it's really just the idea of the Cazul complex. These are, in fact, algebras that are called Cazul dual algebras, and the elementary part of this works very generally. So let's just do it. Suppose you have, let's do it in this direction first. Suppose you have a graded E module. By the way, there's no finiteness assumption here at all. You'll see this has really nothing to do with anything. But it's useful. And I should remark also that these guys had degree, these variables had degree 1, so it's rather natural to think of these functionals as having degree -1. And so the variables in the exterior algebra will have natural degree -1. The exterior algebra, of course, is commutative, right? The commutative law says that A times B is -1 to the degree A degree B, B times A, whereas the polynomial ring, as Dave Benson pointed out to me, is non-commutative. It's trying to be commutative, but only the even degree parts of it are commutative, actually, in this sense. And this is a serious point. This is not an idle remark. The fact that it fails commutativity spoils certain things that would be true over the exterior algebra if it were commutative. So I hadn't understood this until Dave pointed out to me that that was the meaning of the phenomena I was seeing. So we really have been working in non-commutative algebra all our lives. And now at last we're about to graduate to the commutative case. Okay, so P is a graded E module. P is the sum of Pi. And I want to make a complex of free S modules out of P. So I will take S tensor Pi. And, of course, multiplication by one of the elements of W star, I'm going to call these E0 up to ER. That's a dual basis to the xi's. So multiplication by an EI lowers degrees, and the maps here are going to go down. So this will go to S. This is tensored over the ground field. S tensored over K, Pi minus 1. And onward, S tensor over K, Pi minus 2, etc. The degree of the generators here will be I. The degree of the generators here will be I minus 1. So, of course, this map, which will be a map of graded free modules, will be represented by a matrix of linear forms. Let's write down the map explicitly. The generators of this free module are the elements of Pi. So I really only have to tell you where the elements of Pi go in here. So an element, let's say little p, one tensor P with P and Pi goes to summation xi, that's of degree 1 element of S, tensored with EI multiplied by P. Right? Nothing could be more direct and simple. Sorry? They're the same I. They're not the same I. J. Thank you. Summed over J. And now we're supposed to say that this is a complex. So where does that go? Well, that goes to summation over L, XL, XJ, tensor E, L, E, J, P, and this is, of course, summed over J inside. These are over all L and J. That's supposed to be 0, right? We're supposed to have a differential here. So let's just compute. This is equal. Well, let's gather the corresponding terms. The point is that L and J are not ordered here. So if I sum over ordered pairs instead, then I essentially get each pair twice, and these will occur in each order. So this is the sum over J less than or equal to L, let's say, of XL, XJ, tensored now with E, L, E, J plus E, J, E, L times P. And this is 0 by anti-commutativity. Right, so this vanishes. Now, I used the commutativity of the x's here to get things to work right. And I've actually built in associativity as well to make everything okay. So what's true and not very hard to check is that the fact that this really is a differential, that this squares to 0, is equivalent to the commutative and associative laws together of multiplication in S try again. It's the commutative law in S and the associative anti-commutativity in E, which I've used, right, to do this. So that's to say that to be a module over E, that's some assertion about anti-commutativity of multiplication and associativity of multiplication, is exactly the same as for this other thing, which I'll call L of P, to be a complex over S. And now I could do it in the other direction just as well and define if I have an M summation mi and S module, then I get R of M, which you can think of, if you like, and I do think of, as E tensor over K M, but, well, there are lots of terms, Mi E tensor Mi minus 1, K, etc. To make these really adjoint in the nicest possible way, rather than putting E here, you should tensor the whole thing with the highest exterior power of W. That's a one-dimensional vector space of a certain degree, degree R plus 1, and that makes the functoriality better. But I won't even bother to put that in. Or you might take a Hom, which is the same as that tensor product. But this is what the functor is, and I'm not going to use it in such detail that I need that extra precision.
Weren't you going to go between a linear free S complex and a graded E module?
I started with a graded E module P, and I went to a linear free S complex on that board.
Right, and then you said you were going to do the reverse.
And then I started with a graded S module, M, and I went to a linear free E complex. That's this.
Oh, I'm sorry. I misunderstood what you were saying over there. Okay.
Okay. So I can go back and forth. Now, you know, this is kind of nice in a way. Perhaps it's a new view of a module, but it wouldn't be so interesting unless we could say something about the modules, which was interesting for the complexes. Somehow there must now be a dictionary which tells you any property of a linear free S complex, for instance, is some property of an E module. So this is the same as the other, so I will not worry about it. Craig? Yeah.
I mean, this has to do with Karen's point.
Did I do something wrong?
No. It's just if you have the linear free S complex.
How do you go back?
Well, you explained how to go back, but you get a complex, not a module.
It's a little worse than that even, because I might get some wrong complex. I mean, yes, I get a complex. That's right. So these are not inverse in any normal sense. You have to pass to the bounded derived category before you see a pair of inverse functors. You can make them into adjoint functors more cheaply than that. Anyway, I don't need any of that for what I'm going to do. So let me write down a proposition which sort of indicates that something interesting is happening. So why were we bothering to talk about linear complexes? Anybody remember from the last lecture? It was because I said any free resolution over S is sort of an extension, a successive extension of linear complexes. And in particular, I was interested in the linear strand of a resolution, that lowest degree piece of the resolution. So you might ask, when is it the case that a given linear complex is the linear strand of a resolution? Or when is it a subcomplex of linear strand? Or when is it exact? When is it a resolution itself? Those are sort of special cases of a single principle. So proposition 1, let's call the complex L, which I'll write as L of P now, is 1, a subcomplex of the linear strand of a minimal free resolution of a finitely generated graded S module. I hope you understand by now. If and only if P star, now, or let's say P hat, I need a new piece of notation. Over E, there are two different dualities. They're almost the same, but nevertheless, they're formally different. One is Hom over E into E. The other one is Hom over the ground field into the ground field. They really differ only by a shift of degrees, so you don't have to worry too much which is which, but I'll write hat for the second one. So I'll write p hat equals halm over k of p into k. That's the natural duality on the category of, let's say, finitely generated E modules. This is again an E module because E is commutative, really, or anti-commutative. So there's a little problem about which side the ring acts on, but you can move it across. You can move sides. This should be, if P is a left E module, then this should be a right E module. But right E modules are left E modules via the involution, the anti-involution of the exterior algebra, which takes odd degree elements to their negatives. Anyway, that's a refinement, which again we don't really need to worry about. So a subcomplex of the linear strand of a minimal free resolution, if the complex is of the form L of P, if and only if P hat is generated in degree 0.
And finitely generated, I guess.
Finitely generated, yes. E module. Now, if you think about why P hat and why degree 0, remember L of P looks like S tensor Pi goes down, and we're interested in its being part of a resolution, so we'd like it to stop at P0. And then P hat will start with P0. That'll be the lowest non-zero degree in P hat. So this is a reasonable kind of condition to impose. We're supposed to go down to S tensor P0. That's the way I'm thinking about this. So if you like, well, depends what you think a minimal free resolution should be. If you think the degree 0 part should be clearly labeled 0, then this is tautological. Otherwise, let's just assume that the lowest degree non-zero term in P is P0. And then this is the natural thing. So then P hat is P0 dual and P1 dual, which is P hat sub minus 1. And it can be generated by P0 hat. Okay. So second condition, it is in fact the linear strand of a minimal free resolution if and only if P hat has a linear presentation. That means it's the co-kernel of a matrix of linear forms over the exterior algebra.
So the EIs have degree minus 1?
Yes. So by linear presentation, I still mean, well, a matrix of things that look like they're degree 1 in the E's, and therefore they happen to have degree minus 1. That's right. So if you want to write this out explicitly with that in mind, it means that you have E to some power mapping onto P hat, and the next term is E of plus 1 to some power. Right? You expect maps to go in the other direction of the exterior algebra, but that's just because of the sign of the degrees. Third, we might ask, when is L actually the free resolution of a module? In other words, when is it exact? Or I guess I should say a free resolution, if and only if P hat has itself linear free resolution. So its whole free resolution is linear. All the matrices are just matrices of linear forms. So that's sort of an amusing sign that we've done something right, that this is actually going to be an interesting correspondence. All the chalk at this point has become the same size by a process of natural selection. I really should label this third part infinity, because these are three of an infinite sequence of remarks of the same kind. Let me tell you the principle that's behind them all.
Mathematics to assign lanes fairly in bicycle racing and trying to build a model. In fact, Ed Gonzalez is here, and last summer Ed was put on the problem and he solved the problem, but that's not what we're going to talk. Number theory and gear ratios. Why is 411 the most popular gear ratio in the world? Chevrolet has used 411 except for 1 year in 1929 when they went to from 411 they went to 355, then they went back to 411. Can you use mathematics and number theory to say why 411 is such an incredibly good gear ratio for cars? And the answer is yes. Today's drag strip, we're going to talk about it. Can you use mathematics to calculate how you should load a trailer and how it should be? The answer, of course, is yes. But this is what we're going to focus on. Okay. Drag racing. The greatest show on wheels. See, car racing is the country's most popular sport. And within car racing, drag racing is the most popular. And there's a lot of parallels. You saw parallels in what Joseph was talking about, how the 70s were wild. I mean, muscle cars beyond control, beyond boundaries. Music that had become self-indulgent to the point of, musicians playing it for themselves. And society, revolution within society, not coming from people who just wanted to say they came and they weren't happy and very serious, but middle-class America turns upon, so we saw the parallels there. And I'm maintaining drag racing and the birth of rock and roll. So we're going to do the birth of drag racing, and we're going to do, at the same time, it was the birth of rock and roll. So look, drag racing and rock and roll. Born in America in the 50s, went crazy in the 60s. So it's often that you do parallel these things. And so I want to talk about this. Drag racing is the only major sport I know of where women have competed successfully with men. Okay. Shirley Muldowney, world champion, 1977, 1980, 1992. Last week in Pomona, Shirley Muldowney came back out of retirement and beat Kenny Bernstein in the Budweiser King, who had a chance at the championship, but Shirley beat him and knocked Kenny out of there. So Shirley comes, goes, accidents, come back. Laurie Johns, Shelley Anderson. Three women who have been extremely successful in here. So here's a little video on Shirley. There's no sound on this thing. But this is Kenny Bernstein in the Budweiser King and Shirley Muldowney on the outside. And she wins the race. Her crew is very excited. This is Shirley on the outside. Incredibly, outstanding driver, done extremely well. Here's Laurie Johns. Laurie Johns out of Corpus Christi, Texas. Very, very popular driver. She grew up racing go-karts and was a national champion. She's on the outside. That's Dick LaHaye on the inside at Pomona. Laurie John wins the race. That's her mother. Okay. Her mother is quite emotional. Okay. And so Laurie's talking about how, but we don't, there's no sound on this one. But women have won national championships. So it isn't that there's a one class. Just across the board, women have done incredibly well in drag racing. Okay, let's go back to a period. In the birth of an era, it doesn't matter what it is, be it rock and roll, be it drag racing, be it even mathematics. There's a lot of characteristics about the start. And that's why what we see in interdisciplinary activity today. The birth of an era is characterized by experimentation, innovation, ingenuity, creativity, large variances, informality, and much fun. You try different things, and I'm going to try to show you that how it's gone in drag racing. Today, we've converged to something very clean and simple. All cars are the same. Everybody does the same thing. There's no variety in the thing. So it's not as much fun. It's very professional. And I see interdisciplinary activity in science and engineering in the same way. So let's go quickly through a little bit of history. And that's the first dragsters. So this is Dick Crafts in about 1950 at Santa Ana. So it's clear what he did. He took a coupe, it says V8, so it's a 32, 33, or 34 Ford, and he just cut it down, put some speed equipment on it, and he went racing. And this car ran about 100 miles an hour in a quarter mile. And so we're going to see essentially evolution. Very sophisticated. Art Christman in his, this is a Roadster. Notice that Dick Craft had the engine up in front. Art Christman has moved it back. and so essentially has better weight on the rear wheels. And we're going to see evolution as it goes through. Ford dragster, this is Calvin Rice, first car to win the Nationals in 1955. Very popular car in the early 50s, very fast, very quick. This is interesting to me. Joaquin Arnett driving the car, this is 1953, the Bean Bandits. The Bean Bandits were out of Escondido, California. And they were the group of Mexican Americans and some blacks and some people who would drag race. That right there is a pinto bean. It's a frijol, okay? So this was called the Bean Bandits, and there was their trademark right there, okay? And so this was very early, 1953. So the ideas come in. Notice the idea is first, get light. Now here's an incredibly neat idea. For good weight transfer, let's put the driver behind the rear wheels. So Mickey Thompson, who was incredibly creative, said, look, here's the axle. I'll put the driver behind. Weight transfer will be really good. As the car starts to go, it's going to transfer weight from the front end to the rear end. And Mickey also did this thing, very narrow rear end. In fact, trying to make it act like one wheel. Very creative, very successful. Mickey Thompson was murdered a few years back. We won't talk about that, but it is basically he was so successful in his career he was murdered. Here we take off again, having the driver behind the rear end. This is Emery Cook driving the Cook and Bedwell dragster, and this is the first car that was manufactured by a company. And these are called slingshots, where you sit behind. Okay, if putting the driver behind is good, how about this idea? The engine torques like this. So let's have it so that weight transfer will be promoted by having the engine torque. That means that as the torque comes down, it'll go weight on the rear end and lift the front end, but then it's counterbalanced by the driver in front. So putting the engine sideways sounds like a good idea, and that was Jack Christman. Here's Kessler and Gamble in another one. These are 56 and 57. Put the engine sideways. Is that going to be good? Maybe, maybe not. All right. Let's put the engine behind the driver, but not sideways. Here's Hensley and Cook in a roadster about 1958. The engine is back here, stuff, put the driver in front, rear engine car. Another roadster that is very famous, the Speed Sport Special out of Tucson, Arizona. Lyle Fisher driving, about 1960. Very successful cars. Look, if you're going so fast, let's try streamlining. Let's make this thing go good. This is about 1958. Chet Herbert sponsored Streamliner out of Long Beach, California, built by Jocko. So let's make it so that the aerodynamics are really excellent. There's Don Gartless, about 70, another Streamliner. Another idea. Jet cars. Let's put jet engines in them. Here's the Green Monster out of Akron, Ohio in 1958. This is internal combustion jet engine. It's not a turbine. It's not a thrust engine. Basically, it's an Allison. But it has an incredible amount of horsepower, also very heavy. Here's a turbine. Here's a thrust engine. This is Roger Harris. So basically, now we're not doing internal combustion anymore. This is just thrust, but it's still a new idea. Okay, maybe we should go to two engines. If one is good, let's try two. This is the Bean Bandits in Look, you can tell when this was. This is a 51 Ford, so this is about 1951. Notice that Carlos Ramirez is sitting behind the rear end, has two engines here. Here's our group of minority racers, okay? Not 100%, probably 85%. 51. This car no one knows about. No one knows about the fact is that he was sitting behind the rear end and had two Ford flatheads in a row. So there's two engines. We see a lot of two engines. Here's a front engine, which is a Cadillac. The rear one is an Oldsmobile. This is called a Bustle Bum, Lloyd Scott, about 55. Here's from Hayward, California. Two Cadillacs. Driver sits behind. A Chrysler and a Ford, four-wheel drive, about 1960. Two Pontiacs side by side. Mickey Thompson, Pontiac, Pontiac. Okay, let's see how that goes. Lefty Mutersbach, two Chevy injected in line. This is Chet Herbert's car. Two Chevy V8, small block Chevys. Here's Eddie Hill out of Wichita Falls, Texas. And basically he has two Pontiacs side by side. Here's an interesting thing. You notice the front end of the car bolts to the engine. So if the engine breaks, then the front end of the car breaks too. Okay, so the engines were actually part of the chassis. If two engines are good, then Ford's going to be really good. Okay? And there's TV Tommy Ivo. He was on the Donna Reed show, Musketeer. He did really well. 4 Buick engines, okay? 4 Buick engines and 4-wheel drives. Here he's going down the strip, okay? So this is about probably about in the 60s. Now, here's the conclusion of the experimental period. All designs were failures except a single engine slingshot. So basically, the Mickey Thompson designed single engine slingshot was a success. The cars were too bulky, 4 engines, too inflexible, not agile, too hard to control, too heavy. However, the slingshot, where you sat behind the rear end, became too dangerous. The drivers would be critically hurt or killed when machinery exploded, engines, superchargers, rear ends. So in 1970, after a serious accident, Don Gartless, Big Daddy, designed a car that put the noise and the machinery behind the driver, where it would be safe for the driver. So the constraint was safety for the driver. And this is Don Gartless' accident. Okay, the flywheel came apart, cut the car in half. This is Don Gartless. This is the rear end of the car coming over the front end. He was very seriously injured. That's when he said, the driver can't be behind the rear end anymore. It's too dangerous. Okay, so now I go to our humble beginnings. This is the love, one of the first loves that Bobby and I ever, I guess, came up with and nurtured through our childhood and continued to have strong interest in. That's me in 1957 standing next to Bobby's car. Okay, this is my wife Jean about 1960 standing next to the car. Notice that paint's changed a little bit. So that's Jean in probably about 60. Here's the first car we ever built. It's a dragster. And notice it's got motorcycle wheels. It basically has a Chevy V8, 57 small block Chevy V8 that was in that 57. And this is about 1957, 58, that we built this thing in the garage, put it together, and decided that we would go racing. So we have now built a race car, okay? How much did it cost for us to build that race car? Not a lot of money. I mean, we built it in the garage. So we could go racing without spending a lot of money. Now, here's working on the car. Everybody gets involved in things. Now we're going to go racing. We couldn't afford a trailer, so we had to put it in the back of a truck, okay? And so this was our sort of our version of our trailer. We just loaded it up, picked it up, put it in the back of the truck, and went racing. Okay. Here's at the strip. We're getting ready. Now here's what this is a mathematical point. The essence of drag racing: quick versus fast. Fast here I use fast as miles per hour. Quick means elapsed time. How fast do you get there? So I want to use as an example that everybody uses pretty much across drag racing history. This is my brother Bobby, beats Art Arfons in the Green Monster in 1959. Bobby became known as Bobby the Giant Killer. Now, look at this. Here is a jet-powered car that is running about 180 miles an hour in a quarter mile. Here's Bobby with a little tiny Chevy that's running about 140. And yet, at the start of the race, he's already way ahead. This is important. So, Bobby beats the giant. This is sort of like Jack and or Goliath, David and Goliath. Okay, so Bobby goes after the giant car, but it's not really a surprise. And let's try to. So we'll get back to this. Okay, so Bobby becomes a world-class driver. My brother continued to drive for other. After we left the Chevy, he drove for other people, in particular Larry Stellings. So he set the Long Beach Strip record. This is Bobby, and. Doesn't matter who that is, but this was a record run. Okay? Bobby wins the race. Now notice this. Bobby had an ability that A.J. Foyt has. How to stay into a car right at the verge, it's about to lose it, and you're about to essentially create some kind of loss of control. So here's Bobby at Long Beach at the start. Look at those radius rods. Look at this one is straight, this one is bending. Incredible pressure on the front end and twisting like that. But Bobby stayed in it, and he set that record. Eventually, in 1968, in Larry Stelling's car, Bobby sets the world record. Okay, so that's basically success. So here is the fastest elapsed time ever recorded in the world in a dragster. So this was 1 month ago. Today is the 2nd. 1 month ago, October 4th, 2002. Bakersfield, California. My twin brother, Bobby, known as the computerized driver, was inducted into the NHRA Hall of Fame for drivers. Okay, so I think at this point I would just like to acknowledge Bobby. Stand up. Okay. So since he lives in San Jose, he was able to be with us. So let's go about drag racing today and see what's happening. So here's a world record run, April 9th, 1999, by Larry Dixon in a car owned by Don Prudhomme. So let's
competition's underway. Larry Dixon going to work. Look at that elapsed time number. 4.486 seconds. A new national record set in second round qualifying. Dixon in the far lane. If he didn't have a wheelie bar, he wouldn't have turned in that kind of a number. He did. And while we were watching, it took our breath away. And needless to say, driving for the state, it took Larry Dixon's breath away as well.
Front end was up for a long time. I almost shut it off because it was way high for a lot longer than we normally do. It set the front end down and it blew smoke off the tires just like a 747 jet. It was a ride.
Okay, so one of these things when we get in a little bit later on, I want you to see that before you start a race, you have what's called a burnout. And the idea of this is to get the tires really hot so they're sticky and gooey. And here's what the burnout looks like. You put water on the strip, you get on there, you spin the wheels. Now they're hot and gooey. You're ready to go back and race. Okay? So there's a lot of, we're at the edge of the laws of physics with these cars. In fact, the constraints are always put on for safety because you're just pushing the boundary of physics. And so I want to show you some examples. Now, in each one of the things I'm going to show you, no one was hurt. Okay? There were examples, of course, where people were hurt and killed. But none of the runs I'm going to show you, and this goes back to something that Bob Meganson said, no drivers were hurt in these runs.
My back's a little sore, but that's okay. That's racing. Just shows how safe these cars are. And that's why NHRA has all the strict rules, safety rules, just for this reason. I went out there and it started to smoke and shake, and I just barely got out of it. When I hit the throttle, all the clutch locked up and the tires hooked, and over it went. I mean, I was there for the ride, and that's okay. I mean, you're going to go through them racing. I'm fine, so it really, I mean, now I know what it feels like to really crash, and that's okay.
This is a jet car. I know those two words don't normally go together. You'll see why. Houston, we have a problem.
This is Raymond Beadle in the Blue Max out of Dallas, Texas, known for wanting to race. Okay, so he loses the body, so he still wants to stay in the race. Parachute comes out, he still wants to stay in the race. Car won't go anymore. So he says, okay, I guess I've got to give up. So I might as well bow to the audience. Okay, okay, so here's a question I want to ask. Okay, what's the maximum acceleration that today's world-class dragsters achieve in a quarter mile? Okay, that's what we're going to ask. You saw these cars go. What's the maximum acceleration that they're basically achieving? And let's look at the world record run of Larry Dixon. So that's a question we're going to try to ask right now. And we're going to give history on this question. There's an incredible amount of history on it. Historically, there's been an implied belief that 1G is the fastest that a car can accelerate, free fall. So basically, free fall and a car going is essentially the limit. And let's explore how that happened to be. Now, in the popular physics book, freshman physics book by Tipler, there's an example of an instance of this implied belief. It goes from 0 to 60 in a little under 3 seconds. The fastest you're going to get a car to accelerate is to push it off a cliff. Okay? Well, that's wrong. Okay, so look, here's the historical background on the proof of 1G. In 1953, Art Christman ran 140 miles an hour, and this article appeared in the magazine at the time. It says the maximum speed as calculated by formula that any internal combustion engine-powered vehicle driving through its wheels will ever attain is 167 miles an hour. It says 100% efficiency is virtually impossible. The fact that 140 was actually reached is almost unbelievable. So they wrote that in the magazine. Next issue. A good number of readers have questioned what I said. Okay? So we've gone to our consultant, Mr. O.L. Vosberg, who was kind enough to send us the formula, and it is as follows. Okay? Okay, here's Vosberg's derivation of 1g as a limit in acceleration. Okay? So, I mean, he pulls on Newton's second law of motion, which is good. It writes F equals ma, solve for acceleration, equals and the mass is force over weight. And basically, the issue here is that the coefficient of static friction, basically the maximum force that you can put forward on the car, i.e., the maximum force that the wheels can use to drive the car forward, is the weight of the car. And you can experiment by just locking the wheels on the car and pulling on it and seeing how much weight it takes. Does it take more than the car? And physics theory says that basically they expect that the coefficient of friction is less than or equal to 1. So basically, if we have that F over W is less than or equal to 1, then acceleration is less than or equal to g, which is the acceleration of gravity. So that's how he came up with 1g as a limit. Now, he also said, okay, here's the formulas. You know, it's distance equals 1/2 at squared. Velocity is acceleration times time. Put them together. So in this application, distance is 1,320 feet, a quarter mile. Now, he said the reasonable coefficient of friction between rubber and asphalt is 0.7. So he puts mu equal to 0.7, and he turns out with 167 miles per hour. Okay? That's fair. So Navarro says, look, we took Mr. Vosberg's letter to several engineers who immediately whopped out their slide rules, and after a few minutes came to the unanimous conclusion that the formula is indeed correct. Now notice here, what he should have said is that the calculations are correct, not the formula. But he says, notice that by using a slide rule, you could verify that the calculations were correct, not that the formula was correct. So people kept on. In 1954, see, 1g is 9.06 seconds. So free fall. Drop a rock from the Empire State Building, ignore air friction, and you get 9.06 seconds to hit the ground. Car went 899. Now, we can't do that. So the drag racing community theoreticians, the racers didn't care and don't care, okay? The response was from the theoreticians, the clocks are bogus. The clocks, you can't do that. You can't beat 1g, so you had bad clocks, okay? And so there's a lot of controversy came out. A lot of controversy at this time from 1953 to 1956 as to whether a car could go faster than 1g or not. Big yes, no, yes, no, yes, no. This is the car that went 899. Yates and Mickelson. What? Where? Here? No, it's just a picture. It's not. The axle is like this. It's curved. I mean, axles either have like a step to come up or the axle is curved. But basically, that's all that's curved is the axle, the front axle. But anybody gets at least $10 to tell me what kind of engine he's running. That's a hard question. Okay. Okay, so look. In 1956, Roger Huntington, Society of Automotive Engineers, says, look, apparently the tread rubber is sinking down into the tiny crevices in the paving and giving an effect something like a gear drive. I believe that some of our drag boys are achieving coefficient of frictions about 1.1 with big, wide, slick tires. So this is a step in the right direction. Now here's the reality gap. That the dragster world record is 4.48 seconds. It takes 4.48 seconds to travel a quarter of a mile. Okay? Top speed at the end of it is 330 miles per hour. Free fall is 9.06. Look at the difference. Free fall is 198. So dragsters are significant, beating free fall by a lot. This is important. Look at this. In 1954, dragsters attained 1g in terms of elapsed time, how long it took to get there. But it took much longer, 1964, to get 1g in terms of miles per hour. 2g's. This is essentially Bobby, about the time he ran. 6.4. Bobby ran 6.5. So Bobby ran average 2g's for the quarter mile in elapsed time. But it took till 1987 to get 2g's here. We're running 3 Gs, 5.23 in 87. We have not reached 3 Gs in terms of miles per hour. We've reached actually 4 Gs in fact, Larry Dixon in that run you saw is 4 Gs. But we're not going to reach the 4 Gs here. And will we ever get to 5 Gs? I don't know. But so basically we have 4 Gs in acceleration. So dragsters are much better at elapsed time than they are at top speed. Let's follow that through mathematically and see why that is the case. So here's an attempt to better understand acceleration. And there exists a mystique about top speed, but not elapsed time. Probably because the top speed is easier to understand. 300 miles an hour means a lot more than 4.5 seconds. However, as fast as winning goes, this is as far as winning goes, top speed, how fast you're going at the end of the race is meaningless. It's how quick you got there. So we're going to give an illustrative example of Bobby and the Green Monster. So look at Bobby and the Green Monster and see why Bobby was able to beat the Green Monster. 1959, Green Monster, our hero. Okay. So basics on elapsed time versus top speed. So here's what we're going to do. We're mathematical modelers. So basically, we're going to write distance as a function of time. And we know from elementary physics that velocity is the first derivative, acceleration is the second derivative. And the top speed at the end will be the first derivative, velocity, at time it takes to go 1,320 feet. So we're going to look at distance as a function of time. But we don't know what that is, so we're going to have to get some data. So, we'll get back to that. But look, here's the dragster. Here's Bobby. Incredibly fast acceleration, going down to 0. The jet car is the opposite. Very slow starting, gets faster and faster and faster. So the acceleration that is high is all here. Bobby's acceleration is all here. Now, velocity is the area under the curve. So let's look at the velocity for Bobby versus the velocity for the jet car. So it's the area under this curve for Bobby. And notice that there's a lot of area at the start. So Bobby gets to go very fast right away. Then he stops off and goes this. Where the jet car is getting bigger and bigger and bigger, area under curve towards the end. And in fact, the jet car has greater total area, so top speed. But now what we really want to know is how far do you go in a fixed amount of time? And that's the area under this curve, these two curves. And notice that Bobby's going to win significantly. So Bobby is going distance versus time. Bobby's up here, and the jet car is over here, and Bobby finishes way ahead of the jet car. So it's area under curve. So the whole idea is to start to go fast as soon as you can, which is called good acceleration. So the total area under the acceleration curve is greater for the jet car. Hence, it has a larger velocity at the end of the race than does the dragster. However, the car with fast initial acceleration spends most of the time going fast. So the area under the dragster velocity curve, i.e. distance traveled for a fixed time, is much greater, and therefore it gets to the finish line first. So that's a fundamental, okay, right there. And to say, of course we know what we do is get out first. So a car with good initial acceleration will win the drag race. Acceleration is large and it drops off. This explains why dragsters do such a good job on elapsed time and such a bad job on top time. Jet cars will do a good job on top time. Now, if you look at Webster 1, defines drag race as a speed contest between automobiles. Speed is wrong. Okay? He missed the essence of drag racing. Speed should be replaced with acceleration. And in Webster 2, they have done that. Okay? Now, years of experience and observation have led the drag racing community to following the commonly held belief. The acceleration for a dragster is just like we showed in the picture for Bobby. It starts out really high, and then it goes down to essentially to 0. And in fact, you should gear yourself so that basically it is 0 at the end. I mean, that's otherwise you're not using everything you have. So this is basically the common belief that this is what the acceleration looks like. Moreover, the maximum is somewhere between 3 and 5 g-forces. So basically, it's this, and whatever the maximum of that curve is going to be between 3 and 5. So let's look at that. Let us look as mathematicians at that. Let's study these two aspects of dragster acceleration. Maximum acceleration, and is the acceleration monotone decreasing? And we'll learn from that. So we get data. we call the National Hot Rod Association. Give us the data for Larry Dixon's world run. The data comes at the 60-foot time it took to get 60 feet, time to get 330 feet, 660, 1,000, 1254, and 1320. Why these are so close is because they use a finite difference approximation for the time, but we're not going to get into that. Obvious. Now look, there's two other pieces of information that are quite obvious. The distance that you travel at time t equals 0 is 0. Cool. Speed at t equals 0 is also 0. Now that's a little bit not as obvious. Second derivative at time equals 0 is not 0. Function at 0, 0. Derivative at 0, 0. Second derivative, leave it alone. So we have 1, 2, 3, 4, 5, 6, 7, 8, 8 pieces of data. So what do? We put a polynomial of degree 7 through it. Okay? Plot a world record run. Now, say polynomials of degree 7 or high degree polynomials are supposed to wiggle and have extraneous, wiggles and stuff. They're not supposed to be real good. That's why spline theory was supposed to come in and do really good. But this is a beautiful polynomial of degree 7. It's beautiful. Look at it. No polynomial is more beautiful than that polynomial right there. Okay? I mean, it's gorgeous. I mean, it's perfect. There's no little wiggles. Do you not like some spot? Is there any spot in there that you don't like? Okay, so look. So what do? We do something that we know we're not supposed to do. Okay? We're going to interpolate the data with polynomials. So for example, we know that here we have 0 and that the derivative should be 0. So we can put a parabola through the first 2 points asking the derivative to be 0. We can put a cubic through 3. We can put essentially a quartic through 4 and fifth order, etc. So we're going to do that and then calculate the maximum of the acceleration. So we interpolate the data with a polynomial of degree n, asking the derivative is 0, and then we estimate maximum acceleration by maximum of the second derivative of the interpolating polynomial for that particular time frame. If we do, we find out that for Larry Dixon's run, when we take and put a quadratic between the first 2 points, we get a maximum acceleration of 5.07. We do a cubic, 548, it goes up. That polynomial of degree 7 that you said was so beautiful, or that I said was beautiful and you believed, says that the maximum acceleration is 7 Gs. 7 Gs. Now, people don't believe that. 7 Gs. So at the end, we'll vote on whether we believe it or not. Now, here's a theorem. A theorem. Every talk has to have a proof, okay? The estimate of 5.7 is a guaranteed lower bound. Why? Proof. See, a quadratic with the first derivative 0 at t equals 0 looks like that. So that means that when you fit this to the 2 points, what you have done is said, if the acceleration looked like this, this is what it would take to get to that first point. Now notice that the acceleration is constant. So that means, or it's average if you wish, it's average acceleration. Well, the true acceleration maximum has to be better than the average. So the average has to be better than 5.07. So we have a theorem that says it has to be at least 5.07 or bigger. Okay? In all cases, the maximum acceleration occurred at time t equal to 0, right at the start. As the degree of interpolating polynomial went up, we put more curvature into the model, we got as high as 7. What should we expect to be reasonable? I don't know. Somewhere between 6 and 7 seems reasonable to me. Now, Mossberg's flaw, the assumption that in this application mu is less than or equal to 0.7. Indeed, we have to question in some sense, as Roger Huntington led to, is the coefficient of friction less than or equal to 1? We're going to accept that model. We're not going to throw that model away yet. So, it's hard to believe that if we have an acceleration of 7 Gs, that means that the acceleration is 7 Gs, that mu g has to be 7, so mu has to be as high as 7. That means the coefficient of friction has to be as high as 7. That means that basically the force put down on the wheels of the car have to be 7 times the weight of the car. 7 times the weight of the car. Not the weight of the car, but 7 times. That's hard to believe. Can it be that the downward force exerted by the tires on the asphalt is 7 times the weight of the dragster? Well, I found a picture. And the picture is showing you that it's really collapsing the tires. So the thing is, this doesn't say it's 7, but it says, look, you are really abusing those tires.